All right, it's 9:30. Let's get started with our next talk. Next speaker is Sham Dorkish, Monotone Increasing Representation Functions. Please take it away. Do it.
Thank you very much. So in the first part of my talk, I would like to summarize the previous results about the monotone increasing representation functions. And then the next part, I will introduce the recent new results. So my results as a joint work with Csaba Sándor and Yang Chuan He. First of all, I would like to tell you the definition of the representation function. So we consider an infinite set of positive integers, and for a fixed k positive integer, which is at least 2, I will denote r sub ak of n is what I will call unordered representation function, and this is the number of representations of a positive integer n as the sum of k terms from the set A. And I will define two other representation functions that I will call unordered representation function and the strictly unordered representation functions, where the summands are all distinct, and the strictly unordered representation function is where equalities are allowed among the summands. Another basic definition is what does it mean representation function is monotone increasing from a certain point on, and this means that if for every large enough n, the number of unordered representations of n plus 1 is at least as large as the number of unordered representations of n. And of course, for the two other representation functions, the definitions of the same. And I will say this is strictly increasing if equality is not allowed. And another notation is the counting function of a set A. This is a function A of n which counts the number of elements of a set A up to n. So the study of the monotonicity of the representation functions began in the 1980s. The first such results is due to Erdős, Sárközi, and Tésós. They characterize the monotonicity of the sets where the two terms unordered representation function is eventually increasing. And they prove that this holds if and only if only a finitely many integers are omitted from A. In other words, A is a co-infinite set. And they tried to describe or characterize the two others representation functions as well, and they studied them as well, and they proved together with Chen and Tong the following theorem. So if B is an infinite set of non-negative integers with even integers, and then the ordered representation function corresponds to its complement is monotone increasing from a certain point on, if and only if this set B is a so-called generalized Sidon set. And if we have two elements in B such that their sum is large enough, then this sum cannot be in B. Actually, this statement was found by Erdős, Sárközi, and Tésós, but it was mistakenly presented in their previous paper, and they presented correctly in a common paper with Chen and Tong. And they also studied the case, what can we tell about the monotonicity and the density in some sense of the set, and they proved that the existence of an infinite set with less than n minus constant times cube root of n elements for every large enough n, and ordered representation function is monotone increasing from a certain point on. And later they studied this restricted ordered representation function, and they proved that if the set A cannot be too sparse, then if the set is sparse, then they cannot be monotone increasing in n from a certain point on. And on the other hand, they proved that if this the limits of this ratio n minus the counting function over log n this tends to infinity. If n tends to infinity, then this restricted ordered representation function cannot be monotone increasing from a certain point on. And actually, this result was also proved by Balasubramanian independently, in a little bit simpler way. Very little is known about case bigger than 2. This case when we have more than 2 summands in the representations. Tang and independently by me, we extended the results of Erdős, Sárközi, and T. Sós for the k-terms unordered representation function. We proved that this is counting function is small o n over log n to the power of 2 over k, then if this representation function is monotone increasing, then this cannot hold. And Dombey also studied the case when the number of summands is bigger than 2, and he constructed a set such that the k-terms unordered representation function is eventually increasing for every k is bigger than 4, and the density of this set is 1/2. So let me show you the construction, the idea of Dombey. He used the so-called Rudin-Shapiro sets to construct such an A. So a Rudin-Shapiro set is a -1,1 set, which actually a sequence which is defined recursively in this way. So the first element is 1, and the even indexed element is an, and the odd indexed element is -1 to the power of n times an. And Dombey proved that the sets where the n-1 indexed terms are 1, this n is suitable. And it can be proved that the Rudin-Shapiro sequences is well distributed among arithmetic progressions, and this gives the desired density. And Dombey conjectured that if a set is co-infinite, then the corresponding k-terms unordered representation function cannot be strictly increasing from a certain point on. Dombey mentioned that this conjecture is supported by computer experiments, and recently Bell and Shalit disproved Dombey's conjecture, and they constructed a set such that the corresponding k-terms unordered representation function is eventually strictly increasing. So they proved so they constructed a set which does not contain 0, and the number of elements of up to n is small n to the power of alpha, when they gave an upper bound for alpha, namely k minus 2 over k, and they considered this complement, and they proved that this set A is suitable. So their proof is very interesting because they use the deterministic finite automatas, automatic sequences, and logics, and they combined these ideas with a software called Walnut, which is a theorem prover software. The k-automatic sequence is a sequence which is a representation in some number systems. To give this automatic sequence to a deterministic finite automata, the automata is processing on the digits, and then he stops in a state, and as an output, the automata gives the nth element of this sequence. And we can catch a set by using its characteristic function, because it proved that the characteristic function of a set is an automatic sequence. And it's observation what Bell and Shalit applies, and they could construct such a set. And actually, if they prove that there exists a set such that this representation function is not only eventually strictly increasing, but this is strictly increasing from the beginning, and this set F is suitable. So 2 to the power of n plus 2 minus 1. And if we consider this set, and in the previous theorem, then this representation function is increasing from the beginning. And after this, in a common paper, we improved Bell and Schalit's result. We proved that for every positive integer k, which is at least 3, and we have this upper bound from the count to the counting function and the power of k minus 2 over k minus 1 over k minus 1 factorial to the 1 over k minus 1 minus 2. So if we have this bound for the counting function, then the unordered representation functions corresponds to the complement is eventually increasing. And in particular, it is clear that if we consider k is equal to 3, then we have this upper bound for the counting function square root of n minus 2. This was important for us because in this case, we can improve the constant factor, and then we can prove this, that if we have the condition, the counting function 2 over square root of 3 times square root of n minus 2 for every large enough n, then the representation function corresponds to the complement for k is equal to 3, then this is eventually increasing. And we could prove as well that our bound in our first theorem is tied up to a constant factor, or in other words, is nearly best possible. So we can prove the existence of a set of natural numbers such that if we have a function which tends to infinity and we have the bound for the counting function as constant times n to the power of k minus 2 over k minus 1 plus fn for every n, at least 2, then our representation function corresponds to the complement is not monotone increasing. I would like to tell you a few words about the proof. So the first two theorems, we use the generating function. So generating function of a set A is a function considered by the sum of x to the power of a, where a runs through the elements of the set. And it is easy to see that if we raise to the power of k, then this will be a power series, and in the coefficients, the representation functions appear. And the monotonicity we can catch by multiplying 1 minus x, and in our theorem, we consider the representation functions correspond to the complement of a set. So we can catch this by multiplying 1 minus x. And we can also make a connection with the monotonicity and the counting function, because a counting function can be represented also as a power series by using the characteristic function of the set A. And if raised to the power of k both sides, then again the representation function appears as a coefficient on the right-hand side. And by using these observations, we can describe our situation or statement, and we analyze the generating functions and power series, and we get the results. And I mentioned you that we constructed a set which shows that our first theorem is nearly best possible. And let me tell you the proof. So you remember that we assume that we have that bound n to the power of k minus 2 over k minus 1 plus fn, where fn tends to infinity, to the counting function, and we suppose that this function fn is smaller than constant times k minus n to the power of k minus 2 over k minus 1. And we construct a sequence inductively. So the first term is 40. And if we define the first j term, then the j plus 1 term is an even integer such that it is bigger than k minus 1 times the jth term, the power of k minus 1. And fn is bigger than this quantity, than the sum of these elements, the power of k minus 2, multiplying by k minus 1 for every large enough n, namely which is at least as large as the j plus 1 terms. And we're taking the union of these of these sets, so the multiples of nj's, and it's up to k minus 1 times nj is to the power of k minus 1, and this set will suitable. And then simple computation shows that the counting function is smaller than our bound in the theorem what we stated. And actually, Shalit also proved the existence of an infinite set such that the representation functions, three terms representation functions corresponds to the complement is strictly increasing, and its lower asymptotic density is 1/9. He also used deterministic finite automatas and logics to construct such a sequence. And recently, he mentioned that this holds for not only for 3 but for k, that this is the order of magnitude of this representation function n to the power of k minus 2. And recently, Shandor and Young improved their result, Shalit's result, and they proved that if we consider a set of integers such such that the first two digits of these integers in the number system of base 4 is 1 or 2, together with the 0, then for this set, the order of magnitude of this difference is n to the power of k minus 2, where the implied constants depends only on k. And furthermore, Dombey also studied the density of the eventually increasing representation functions, and he asked whether there exists a set such that the corresponding representation function is eventually increasing and its density is alpha, where alpha is not equals to 1/2. And Shandor and Young also constructed a set such that its density is 1 recently, and the k terms representation function is strictly increasing. So actually, this previous set B is not suitable because they computed that the lower asymptotic density is 2/3, the upper asymptotic density is 8/9, so that limit, the density does not exist, but they constructed another set with density 1, and this representation function and strictly increasing. They use a very nice idea about the convolution of representation functions because it somehow preserve the monotonicity. So these were the recent results. They did it just a few weeks ago. So that's all I wanted to tell you. Thank you for your attention.
Thank you, Shandor. Uh, yeah, so you mentioned this result from Shalit and somebody through automatic sequences.
Yes.
But I don't see how the bound on the counting function of A doesn't seem to be enough to guarantee that the sequence is automatic.
This here.
Yeah. So I'm just I'm surprised that
I think they managed to prove that this is an automatic sequence by using Walnut. So it's a software.
yeah. Uh, and so is that how recent is that work from Sha?
Well, I think in 2022 they did, and later we improved their results.
And your improvement isn't through automatic sequences though, huh?
In this one, I think we haven't studied yet that this is it gives an automatic sequence, but maybe.
Uh-huh. So thank you very much, Shandor. Uh, are there other questions? All right. So thanks, Shandor.
Okay.
Our next speaker is Dennis Eichhorn at 10. So we've got a 10-minute break. Yeah, this is a nice circle of problems. Shandor, I wasn't aware people were working on these.
Ah,
Just,
yes.